Okay, so welcome back. At least 3 of you pointed out that I messed up this protocol, so let me correct myself before we continue, and then it's a good warm-up after the break. The mistake that I made, so this is not exactly the protocol that Andrew Childs introduced. The part that I got it wrong is at the end here, where the verifier is telling the prover whether it should apply this phase correction or not. Whether it should apply the phase correction or not, as I correctly explained, depends on the one-time pad keys, what these A prime and B prime were before. Depending on these and its knowledge that a T-gate was applied, the verifier determines whether a P correction is needed or not. So whether a P correction is needed or not depends on the keys. And so telling the prover whether the correction is needed or not reveals information about keys in prior rounds, which is a little bit of information that I don't want to reveal. So I'm sorry I got that wrong, and let me explain how it's corrected. So there's kind of a silly trick. So let me, if you don't want to worry about this, don't worry about it. But if you want to worry about it, here's the silly trick. So what's going to happen here is that the verifier is has this one qubit, and it's going to determine should a P correction be applied or not. Okay? If it needs to be applied, it's going to tell the prover, here's the qubit, please apply the correction. The prover will do it, send the qubit back. Okay? If the correction does not need to apply, the verifier is going to create a dummy qubit in a random state, give it to the prover, tell it, please apply the P correction, send it back. Okay? So in all cases, the prover applied the P correction, it's just that it didn't know if it applied it to the computation qubit or the dummy qubit. When the verifier has received the qubit back, in case it was the computation qubit, the P-gate correction has been applied and we just continue with it. In case it was the dummy qubit, we trash it and we continue with the computation qubit that had been set on the side and to which the correction has not been applied. Okay? So I just wanted to correct myself, sorry about this, yes?
You need to assume some memory in addition, right?
2 qubits. Yeah, 2 qubits. Yeah, thanks. So let's continue. I want to mention, in case anyone arrived at the break and who was not there before, if you want to catch up on the slides, I put them on my website. So you can find my name, go to the webpage, and then go at the name is Vidick, Thomas Vidick, and then go at the top right, and there's a link there to a PDF. And at the end of the PDF is a slide that has references, in case you want to look up references while the talk is going on. Also, if you just want to catch up on stuff that we did before, you can quickly browse through it as we're getting started here. Yeah? Sorry?
Does the prover in this example know C, the circuit?
No. Oh, the circuit. Well, yes. So compared to what I was saying earlier, you have to think of this as the universal circuit that everyone knows, and this as the input that actually contains the actual circuit that I want to run. But in this case, it's a bit stupid, but yeah. So yes, the circuit is known. I'm trying to hide the input. Thanks. Okay, so we want to do one more layer on top of this in order to make the protocol verifiable. It was blind, it wasn't verifiable. And let me just warn you a little bit that the next 2-3 slides are maybe sort of the most technical. They're not going to be more technical than what we did, but just like to encourage you to hang on. It's right after the break, you have caffeine, so try to pay attention. And then it'll get a little bit lighter, I think, later on. So what's the idea for authentication? Just as before, we have this one qubit here. But instead of just encrypting it, hiding it using the one-time pad, we're going to do a 2-step process, where at the first step, we concatenate a bunch of what are called like trap qubits. I select a certain number of trap qubits. It's always like half of them are 0, half of them are plus. The number I select is just going to be a security parameter in my protocol later. So the first step is to do that. And then the second step is to apply a random Clifford circuit to all 2k plus 1 qubits. For states of that particular form, you can think of these two operations. They're similar to if I had concatenated random BB84 states and then randomly permuted everything. So it's basically going to have the same effect. It's another way to think about it. Okay, so this the verifier does. It's a bit more complicated now. Instead of just having a single qubit operation, it needs that many qubits operation. K is going to be like a security parameter, so maybe like 20 or something, or 40 would be a good number. Okay, so I do that one qubit at a time. So each qubit gets concatenated with its own trap qubits, and gets applied its own independent uniformly random Clifford on k qubits. There's only something like k squared Cliffords on k qubits, so I can just do that myself if I have a k squared size quantum computer. The point is that k doesn't depend on the size of the actual circuit that I want to run. So this is blind because a random Clifford is more general than applying a one-time pad. So this Clifford is doing the one-time pad plus a random permutation, so it's definitely going to be blind. The reason we're using the Cliffords is that something known as the Clifford 12 that I'm going to flash on the slide, and it says the following. This is the main reason why we're applying a random Clifford. So it has this property. It has the property that if you start with an arbitrary state, so think of this whole here as the whole thing here, right? So it's any number of qubits. And then I apply to it a random Clifford. So I conjugate by a random Clifford. Q is my random Clifford. Okay? On top of that, I apply an arbitrary unitary. So think of this as some kind of bad behavior that the device might be trying to implement on my qubit. So it's an arbitrary unitary. And then I again apply the same random Clifford in reverse. So the star there is for conjugate transpose, is just the inverse of the operation. So this would be the decoding, right? So I encoded whole by this random Clifford. Someone applied the unitary, then I decoded. I average, this C should be a Q, I'm sorry. I average over all possible Cliffords Q. What does that look like? Well, it looks like a constant multiple of my original state that got decoded, plus a weighted combination of the original state to which was applied a uniformly random Pauli operator, where uniformly random Pauli is like on each qubit you apply a uniformly random x or z or x times z. Okay? So it's called Clifford 12 because it says that whatever unitary you try to apply on the outside, on top of the encryption, which is the thing that you, or the authentication, which is the thing that you're going to be given, when the verifier later tries to undo the authentication without knowing whether U was applied or not, the effect of this U lies outside of your control. It's going to look like with some probability you didn't do anything, and with some probability you applied a random Pauli. You couldn't have applied like something that you control if you don't know what the Clifford operation is. This is useful because a random Pauli applied on the state of that form is going to flip some of the traps, right? If it's a random X, then with probability roughly half, it's going to act on the left and it's going to flip this. If it's a random Z with probability roughly half, it's going to act on the right and it's going to flip this. So this is saying that any unitary that I try to apply on top of the authentication either is going to have no effect at all, this is this part, or the effect of a random Pauli, which I would be able to check by looking at the traps. Okay? That was not the case on the one-time pad, right? One-time pad, I could apply an arbitrary unitary on the outside, like H, and the effect would be applying H on the inside. H is not a random Pauli. This Clifford there, this conjugation that's happening with the Clifford is randomizing this unitary, making it look like a random Pauli, which means that the only kind of bad behavior that we have to deal with from the point of view of the device are random Paulis. And that's easy to deal with when we have these traps that we can check. Okay, so let me explain how we use that in the running example again. In order to have the verifier check these traps, I'm going to change a little bit the protocol we had before. And now the verifier is actually going to apply the gates itself all the time. The device is just going to act as a memory. Okay? So here's how the protocol would look like. I would take my qubit 0, but then I not only I not only encode it using the one-time pad, but also I add a 0 trap that's encoded, a plus trap that's encoded, and in real life I would put a few more traps and I would randomly permute these qubits. Okay? I didn't do it on the slide, but I would have to do that. And then ship all that to the device. Everything is one-time padded, device doesn't see anything, it hangs onto it, and then I tell it, well, okay, like, look, now it's time to apply the first gate, so give me back the qubit. So if it was a circuit with more qubits, I would tell it which qubit I need, but here there's just one qubit, so it just ships it back to me. Now I want to apply the gate. So how do I apply the gate? Well, what I'm going to do is I'm going to decode. I know these things, right? So I undo all these things. That's just like single qubit Paulis. Then I apply the H gate to the computation qubit, and then I re-encode everything, and then send it back over, right? And then that's it. That's the whole protocol. I'm going to get it back. Then the next gate maybe is a T gate. Like, fine, I just decode everything. There's no problem of the T gate commuting or not commuting because here the verifier is applying the gate. So it's even simpler in a way, this protocol. And then that's it. At every step, I check the traps and I measure the output qubit. So this protocol is blind and it's verifiable, and it's straightforward. The reason it's blind is the same reasons as before. The reason it's verifiable is because if at any stage the device does anything to the qubits, like any kind of thing, it's supposed to do nothing, right? So if it does any kind of thing, here, when I decode and I encoded before, the combined action of my encoding, the prover's attack, and my decoding is going to be that a random Pauli that's outside of the control of even the device has been applied to the whole state. And because it's random, even the qubit on which it acts is random, and so there's a chance it was one of the traps, and I'm going to detect that. So any deviation gets detected. Yeah? Loud.
Isn't there a problem with that you are telling which qubit to act, so some other packaging is not so relevant because it's very important that
No, I am not telling it which qubit on which to act. So each qubit, so let's imagine this has many wires because it's a circuit that has many wires. Each qubit on each wire is encoded independently using its own code. What happens later is that I do tell the device I need the whole authenticated stuff that's associated, let's say, with the third wire in my circuit. So they learn the third wire. Is that what you're worried about? Were you there in the first part of the talk? Ah, okay. He was not there in the first, but everyone else knows, right? Okay, so the reason is, but it's a good question. The reason is I switched a little bit what the verifier tries to hide. So I'm thinking that the circuit is actually a universal circuit, that everyone knows what the circuit is, but the verifier's circuit is encoded in the input to the universal circuit that tells what circuit the universal circuit is supposed to simulate. Does that make sense? Or? So there is such a thing as a universal quantum circuit that everyone knows. It doesn't depend on anything. But for every circuit that you actually care about, you can specify an input to that universal circuit such that the universal circuit on that input is going to give you an outcome that is the same as that circuit evaluated on 0. Oh. No, so here the prover doesn't act on any qubit at all. He holds on to them. He acts as a memory. So earlier, maybe that's confusing you. I don't know if you were there at the end. Earlier we had a protocol. Okay, so earlier we had a protocol where. So let me say, earlier we had a protocol where the device was actually acting on the qubits, and the verifier was only needed when we needed to do some updates to the keys and these corrections and things like this. Here, the verifier got more complicated than the earlier protocol in two different ways. And that makes this protocol worse, but we're going to see how to make it better again. So there's two ways in which it's more complicated. One way is that it needs to apply this random Clifford that I talked about, this random permutation. And so it needs to create all these qubits at the same time and then apply the random permutation and send them. Actually, it could do one qubit at a time. But later, to do the decoding, it needs to receive all the qubits are associated with one authentication at once. So it needs a bigger computer. For epsilon security, it needs log 1 by epsilon qubits. So that's a bit bigger. And on top of that, it needs to do the decode. That's just applying Pauli's. That's as before. Check traps, that's just measurements. That's as before. But yeah, apply the H gate. And if it was a T gate, it would be apply the T gate. And now I need my verifier to have the ability to apply a T gate. So I'm putting more weight on the verifier right now. We're going to get rid of that. Is that okay? Or? Okay. Yeah?
Is this random Clifford being applied to each qubit individually?
No, all of them. All of them. Yeah. Okay, so but that was a good point, in that in order to achieve this verifiability, now the verifier is doing a lot of stuff, right? I mean, there is a lot of communication going on, and it needs to be able to apply any possible gate, even though it's only one qubit at a time. And so now I want to get rid of that and simplify the protocol while keeping the fact that it's blind and verifiable. So as the next stage, And how we do that, we're going to try to use the same idea as before. So what was the idea that we had before is that if we considered only the one-time pad, this allowed what's called transversal evaluation of Clifford gates. So we can apply it on top of the one-time pad, and we understand how it actually behaves inside the one-time pad. And we'd like to do the same thing with this authentication, but this authentication is a bit more complicated. It involved application of a random Clifford. Oh, I'm sorry, this is just a picture. I see. This is just a picture of what would happen if you, okay. Sorry, I forgot about this picture. I mean, it's just saying that if you want to apply an H on the clear qubit, you can do that transversally on the authenticated qubit because you just apply it outside everywhere and on the computation qubit, because the device doesn't know how they're permuted, right? So you have to tell it to apply H everywhere. And on the computation qubit, it just commutes the way we know before. And on the trap qubits, it also has a predictable effect. It's going to switch the 0 traps to plus traps, and the 1 traps, the plus traps to, this should be a 0 to 1 traps or 0 traps, and then the corrections there are going to be updated. So in fact, Clifford gates we can still do on this code. And so I'm again running through the example here. Let's say we had a circuit that only has Clifford gates. So to go back into the question at the back, so where now the device implements the computation itself. So it got the qubit. Instead of shipping it back to me, so I'd apply the Hadamard, I'll just tell it to apply the Hadamard on all the qubits because it doesn't know which one is the computation, so I just tell it. That's part of the universal circuit thing. It applies it to everything. And on my mind, the verifier, I know this is what happened. Like I can compute, I know what the one-time pad is. Classically, I know this is what happened. So I'll update my keys the way they should be updated, all of them. And then that's it. There's not even any quantum communication that's needed, or nothing. I just told it to apply the gate. It did it, and I updated my keys. And then let's say the circuit only has Clifford gates, so like stuff happens. At the end, I want to obtain the outcome, so I tell it, well, measure the output qubit. Now this output qubit is authenticated, so there's a bunch of them, so it just measures the whole authenticated thing on all the qubits, and it tells me what the outcomes are. And what I'm going to do is I'm going to check, I hope I wrote the same thing, I'm going to check the traps. So in this case, if this was the device's qubit, and it gets measured in the computational basis, I think there's an H there, so H plus is 0, and then there's X, so this is actually B3, this qubit. And so if it measures, it tells me U3, and I check that this U3 is equal to what I think the key is. Okay, well, don't worry too much about checking exactly what the check is. You check that the traps that you could check, which are the ones that are in the computational basis, it gave the right outcome. And if that is the case, you decode the outcome that's supposed to be the outcome of the computation by undoing, so the Z doesn't do anything because you measured in the computational basis, and the X you undo using the X key that you have for the first qubit, and this is this A'1 here, and you return that. So that protocol works for Clifford circuits. It's nice because now the only quantum communication that takes place in the protocol was at the first round. I prepared my qubits, authenticated them, and shipped them to the device. Later on, the device just does everything on its own. I wrote here, I tell it what gates to apply, but because it's a universal circuit, it knows what gates to apply, so it just does it. The only thing is that the verifier tracks the updates to its keys throughout the circuit classically, and at the end, the device reports a measurement outcome that the verifier checks.
One question. Why don't you have to, upstairs, why don't you have to rekey like you did or re-encrypt like you did in the earlier protocol?
Because you can think of the whole, because of the fact that there is no interaction, I can get rid of the interaction. So I can, okay, so now the question is, how do you analyze this protocol and show that it's, well, blind is pretty clear because I didn't send anything, so it's blind for the same reason as before. Why is it verifiable? Well, we have to model what an arbitrary device could do. And an arbitrary device received the qubits, and I can always model this as applying the correct circuit and then applying an arbitrary unitary. Right? In general, I do something unitary, but arbitrary unitary, but an arbitrary unitary is always like the correct circuit, then the inverse of the correct circuit, and then the arbitrary unitary, right? So I can always think of it as the correct circuit times an arbitrary unitary. And so now I can apply this Clifford twirl idea to the whole protocol just at once. So I had authentication on the first step and decoding on the last step that I did on top of the measurement, and that just twirls the whole attack just at once. This works fine. It's going to be a problem in just a second. Yeah? Where's what? Okay. Oh, it happened between the first step and the last step. So at the first step, because I didn't write it, but I apply a random Clifford to this. And sorry, I lost where you are. Oh, I'm there. At the first step, I apply a random Clifford. At the last step, I de-apply the random Clifford, except I de-apply it after the computational basis measurements. I only need to de-apply the X part and the permutation part of it. Oh yeah, that's true. So it's a bit more complicated than that state here. Yeah. Oh, I see what you're saying. I think for the purposes of this, we can think of doing a random permutation. And for the purposes of next, we're going to do the random Clifford everything. So maybe just wait until the next slide. Sorry?
I missed the part from updating the A1 prime, B1 prime, and to the check U3 equal to A3 prime. What happened in between those two steps?
Here and here?
Yeah.
Nothing happened. I mean, the device measured and returned the outcomes of the measurement.
But then the prime, the new size of K never really used at all. Is it used?
Which one has not been used?
A1 prime, B1 prime, A2 prime, B2 prime. How are they used?
Some of them are not used. Like A2 prime here was not used because this corresponds to the key on a trap that's with the Hadamard is a plus-minus trap. And so that is not something that I check when I measure in the computational basis. So here I didn't use it. But if the circuit was more complicated, there might have been other Hadamards later that make me use them. Yeah? Yeah?
Regarding the Newbank Clifford twirling,
Okay.
what it's doing is a bully twirl instead. So you heard the way you've written it out, it's doing a bully twirl under the
Okay, yeah.
but that keeps it in the tensor product state.
Okay.
But it still has, there's an equivalent relationship like the Clifford.
Yeah, right, okay. Okay, right, okay. Okay, so Joe has a better answer to your question, which is that you can analyze that specific protocol just using Pauli twirl, and you don't need the Clifford for that protocol here. We're going to need it next, so let me, this was like an intermediate stage, because it's only for Clifford circuits. We want to do general circuits. And the general circuit, okay, so I should have analyzed the previous circuit using the Pauli twirl. General circuit is going to require we're going to use the Clifford authentication, and that only allows transversal application of just Pauli gates, because Cliffords conjugate Paulis in a predictable way, but not even other Cliffords. And so here I'm not going to give you more detail because it gets a little bit more technical, but this is all in the Aharonov et al. Paper. They have a slightly more complicated authentication scheme than Clifford authentication. It's called polynomial-based authentication scheme. It's based on polynomial-based error-correcting codes. This allows you to perform transversal application of Clifford gates, but you still have to deal with non-Clifford gates, like the T gate, or in their case, they look at the Toffoli gate. These gates cannot be applied transversally, but they give a method in order to apply the gate, so that the device can apply the gate, and then the correction can be done using only classical communication. So it's sort of an authenticated version of this T plus P correction little protocol that I described to you before. It's a little bit more complicated. In particular, it looks something like this, not even quite something like this. I just pulled up the figure to give you a sense of how it would go, but it requires one extra ingredient, which is these magic states. Magic states are just single qubit states that can be, it's the state there at the bottom. So for example, it's a plus to which you apply the T. The verifier is supposed to do this, the bottom part. A T and then maybe a P, Z, X. This is just to hide it. And the, this magic state is also authenticated and sent to the device. And that gives you a way for the device to transversally apply T-gate or TOEFL gate by using the magic state, making certain measurements, like the one that's here, reporting these measurement outcomes to the verifier, and the verifier checking what these measurement outcomes are. But at that point, I'm giving you this like at a too high level so that you could follow if you hadn't seen it. It's just that if I wanted you to follow it, we would have to take like half an hour to do it, and I want to talk about the other models. So the only thing that I wanted to do is sort of the intuition that we had when we analyzed the child's protocol carries over there. And let me summarize the kind of protocol that you get. So it's going to look like this, what we described before. The verifier is going to send the authenticated qubits one by one. And here I wrote the fact that the input is some description of the circuit that you want to run, and also some authenticated magic states that are prepared independently and that are going to be required for applications of T-gates or TOEFL gates in the computation. So to apply Clifford gates, that is done in the same way as we described earlier, because the authentication code that's used here is not the Clifford code, it's this polynomial code that allows you to apply Clifford gates transversally. So the server just does that. There's nothing for the verifier to do except update its keys, which it does. Non-Clifford gates are a bit more complicated. They require this little gadget that was sort of sketched on the previous slide, where the server is going to use one of the authenticated magic state. So it knows these are authenticated magic states. It doesn't know what the magic state is, but it knows that it's meant to be used for the application of a TOEFL gate. And so it uses that. It applies the gate using those. It makes a certain measurement afterwards and reports the outcome of that measurement to the verifier. So that involves a little bit of classical communication. The verifier is going to check the outcome of that measurement, and if the checks go through, then it's going to proceed with the execution of the protocol until the end, where the server is going to, the prover is going to measure all the qubits, report the outcomes. Again, the verifier checks the traps and decodes them. Okay. So this became a little bit higher level now, but it's just to give you a flavor of what the protocol looks like. And to return to Toby's question up there, the analysis of this becomes more delicate because there's all these rounds of interaction in the middle. And so it's not clear how much of this Clifford twirl or the new twirl that would come from the polynomial code can be done in between different interactions, because you only check subsets of the computation at each step. And so there's a little bit of a lengthy proof there that manages to push back any kind of deviation that the device could do at any step in the computation to a deviation at the end, and then use similar kind of analysis that we had before, but it's a little bit more involved, so I'm not getting into it. Okay. Oh, well, okay, this we argued already, so I wanted to argue the properties of this protocol. So blindness, this we're not worried about from the start, right? We have the one-time pad on top of everything, so that's fine. The server just like sees. We have to make sure these classical communication rounds also look uniformly random, but they do. So the protocol is perfectly blind. And the verifiability is what I just described orally now. So I'm going to skip it because the proof of that is a little bit more technical. So let me summarize where we got at. This was the first sort of set of protocols that I wanted to consider, protocols in which the verifier has the ability to prepare and send single qubits in arbitrary, almost arbitrary bases. In fact, more than single qubit. In this case, we needed log 1 by epsilon, like 20 qubits or something, in order to apply this Clifford or polynomial-based authentication. One question that you can ask, so I'm going to list a few open questions as we go through that I think are interesting questions. Here's one. One thing that you can ask is that this protocol involves many rounds of classical communication. If you remember at the start, I said that communication is one of the things that we'd like to minimize. It's very inconvenient to have to interact repeatedly for every single gate with that server. Can we get rid of this? So it's known how to do that. There's a paper by Alagic and co-authors that it does this in a slightly more complicated scenario. The scenario of quantum homomorphic computer is a slightly different scenario. And their protocol just has a single round of quantum communication from the verifier to the prover. Then the prover does the whole computation and then reports the outcome. That's it. No intermediate classical computation. What you lose, though, is that the guarantees now are only computational. So you need to make a cryptographic assumption. Something like learning of errors problem is hard. And so that's why I'm not going to describe that in any more detail. It's an open question whether you could take the kinds of protocols that I've been describing so far and implement them with, let's say, a constant rounds of communication, not like communication at each check of a T-gate or a Toffoli gate. Okay, in terms of the complexity of the verifier, are we happy or not? The protocol that I described, I'm not super happy because of the fact all these traps, and that requires, it's only a Clifford computation, but still it's on this log 1 by epsilon qubits. That scales with the security parameter. Now I need like a 20 qubit computer, and that's getting bigger. The protocols that I'm not describing that have a similar flavor but work in the measurement-based model are a bit better in that respect. So for those protocols, the verifier only needs to prepare 1 qubit at a time and send it to the device. There's not this overhead. You can get away with a single qubit computer for the verifier. I'm not going to describe those. A last question that's a little bit of a subtle one is the question of fault tolerance. Can you implement these protocols in a fault-tolerant way? So there's two different questions. One is, do I need the device, the prover, to be fault-tolerant? And the answer to that is yes. I mean, it's implementing, in general, like a full quantum computation. I need it to be fault-tolerant. But I'm thinking of this as a big server, and so let's hope it's fault-tolerant. But then there's also the quantum computation that's happening at the verifier. This verifier has a very small quantum computer, and so this small quantum computer might not be fault-tolerant. So you can ask, is that the problem? One thing that you could do is say, well, okay, I mean, fine, like, let's just make it a little bit bigger, this small computer, and encode the qubits before we do the authentication and everything in an error-correcting code and ship that over. That would almost be fine, except that your error model might be such that because you might be worried that, so if you suppose that the errors are completely independent from the encryption and the authentication, this is fine. But the problem in general is that the errors at the verifier might interact with the authentication and the encryption in a way that leaks information about the authentication to the device. And so it's not known how to make this fault tolerant at the verifier in a general error model where the errors might be adversarial and might be used to leak some information about your one-time pad keys to the device. I think it's a delicate question to look at. Okay, but I'm going to move on because we have some more models to talk about. I mean, if there's a question, I can take the question. We're going to do something a little bit different now, but that's going to build on what we did, but it's going to forget a lot of the details. Okay? So if you got lost in the authentication, you can hang on now. Now I want to move to our first setup where we have a purely classical verifier. Okay? Get rid of the quantumness completely. And we're going to lose on the prover side. For that, we're going to have to assume that so we're sitting here. We did that first step, and now we're doing the second step, which is I'm going to imagine that this prover can be split into two parts, such that I can do bell tests in between these two parts, and I'm going to explain to you how using bell tests, like CHSH tests, bell inequality violations, how I can bootstrap that all the way to checking that the device is implementing a computation and not just demonstrating a bell inequality violation. Okay, so in order to explain how to do that, I have to just take a little, go back a little bit and explain sort of basics of what's known as self-testing. So usually this is formulated in the language of games. So just for this slide, I'm going to think a little bit of there's no computation right now. The verifier plays a little game that we can think of as a test that's going to be executed in the protocol with the two devices. And now I have two devices that are assumed to be spatially isolated, are cooperating together. They know what the universal circuit is, they know what's going on, but they can't exchange information for the duration of the protocol. In particular, each of them only sees the question that it's, or the data that it's being sent, but they may, and in fact will need to share entanglement. So CHSH game is sort of the most elementary game that you can play in that setup, and it works like this. The verifier chooses a pair of random bits, x and y, and he sends x to the first prover and y to the second prover. These provers are supposed to make a measurement on their state, but whatever, right? So they do something, and they reply with just a bit. So this verifier is classical. It's only exchanging bits with provers. And the verifier is going to perform a little check, which is that it's going to check if the parity of the outcomes is equal to the AND of the inputs, okay? So if X and Y were both 1, then the two answer bits should be different, their parity should be 1. And in all three other cases, the parity of the answers should be 0. They should be equal, these bits. Okay, and what's known about this little protocol? Two things. One, I'll call the completeness. So it's known that you can satisfy this test with probability roughly 85% by having an EPR pair, measuring the EPR pair in the required bases. So these are just sigma x and sigma x and z bases for the prover 1 and some rotated versions of these for the prover 2. Well, I'm not even saying because it's sort of besides the point, but one of the reasons people study this is that if they don't have entanglement, then the best success probability is lower. It's 3/4. And so people use this as a test for entanglement, just repeating this many times, evaluating the success probability. And if it's anything above 3/4, then you have a proof that these provers were using entanglement, assuming that they did not violate the no communication assumption. Okay, but what's interesting is the soundness guarantees of the protocol. So if they succeed with probability close to 85%, not only they must have been doing something that's not classical, which is where usually people stop when they present this in the foundations of quantum mechanics as a test for doing something that's not classical. What's a little surprising and what has emerged in the sequence of works that I forgot to cite, but starting from Werner and Sommer in '88 and many follow-up works, is that you can get a lot of mileage out of this very simple observation that you just ran this test many times and observed this, checked the condition and observed that it was satisfied close to 85% of the time. In particular, you can get consequences on the actions that these provers must have been doing. It's not only that it is possible to achieve 85% success in this protocol by measuring an EPR pair in the X and Z bases, but in fact, it is that the only way to succeed with probability close to 85% in that protocol is by measuring an EPR pair in the X and Z bases. Okay. Up to what's called like a local unitary degree of freedom, because by observing only classical data, of course, I cannot imagine if this prover has like a very complicated state, but then applies a unitary to make it look like an EPR pair, measures it, and then again does something very complicated. Like these kind of local degrees of freedom I don't have access to, so the only statement that I can make is up to an appropriately chosen rotation at the prover's side, this prover has been measuring an EPR pair in the basis that I wanted to measure it. Okay. So that's referred to as rigidity often. It's a very striking statement. This exists only in this kind of thing, and it only exists in quantum mechanics. I know exactly what this prover has been, must have been doing. And so here's one consequence that's sometimes called steering. The consequence is that if I do this many times and I check the statistics, but then the last time, I only do it with P1. Like P2, I don't tell him anything. P1, I send an X and I get an A back. Okay, because I've checked that they've been winning so far, most of the time I can apply some kind of martingale argument and know that, I mean, if I was to run the test at the last time, they would also win. And so I know that P1 has been measuring half an EPR pair in the X or Z bases. But if that's the case, what does P2 get? Well, P2 gets either a 0 or a 1 or a plus or a minus qubit, depending on if I sent P1x equals 0 or 1, and depending if it replied the outcome 0 or 1. Okay? So suddenly I have a leverage on the qubit, on the state that P2 must have for these guys to be succeeding in the protocol, just at that stage, right before I would send it its question and it would execute the CHSH test. And P2 doesn't know. No information got to it right now, right? I just talked to P1 and told P1, please play CHSH. And in fact, what I'm telling it is like, measure your EPR pair in X and Z, or Z, because that's the only thing that would allow you to win CHSH. And so that basically gives us the building block that we needed to apply the other protocols. If you remember the other protocol, mostly this is the only kind of stuff that they need you to do, right? They need the verifier to have the ability to prepare qubits, these traps that look like 0, 1, plus or minus, without the prover knowing. And there was a little bit more, right? So there was the Clifford and there was other things, but at a very elementary level, that's the one thing that we need. And here's how we can achieve it without having the verifier to prepare any of the quantum things, just by doing these EPR tests and then stopping at a certain point, and we know that this guy has these qubits. Verifier knows, prover doesn't know. And so that's really the thing that we need to get started. Yeah.
And so the question of where are the qubits is also sort of answered by this.
Exactly, right. By these, the previous slide, these self-test or rigidity statements that say that assuming quantum mechanics is correct, but not assuming that there's any qubits that you control, if you succeed with high probability, then you must have, there's a well-defined qubit in this P2 that it's a well-defined state, 0, 1, plus or minus, that the verifier knows, and P2 actually doesn't know, because it doesn't have the information that was sent to P1, and that's like what plays the role of the one-time pad keys now. Thanks. So we need a bit more, right? Because we had this Clifford, etc. So we need to, this so far is just testing one qubit. Now we need to test many qubits, and we need to be able to test that these qubits were initialized in like Cliffords, etc. So this I'm going to skip over a little bit faster, but the sequence of works does such tests that bootstrap the CHSH test to not just checking one qubit in BP84 states, but n qubits in tensor products of not only 0, 1, plus, minus, but also eigenstates of Clifford observables, which is the thing that you really need in order to be able to apply the earlier protocols. So the test looks a little bit more complicated. It's like playing CHSH in parallel many times. It's a little bit more complicated than that. But the upshot is that you can do it. And you have similar kinds of statements, which is that if they share APR pairs and they do the right thing, they can succeed. And 85% got 1 here. For those of you who care, it's just a convenience. You replace the CHSH game by this magic square game. That's another type of test that has similar properties. But now the quantum guys can win with probability 1, which is just like something that's easier to test when you're doing the statistics than like this 85% thing. Okay, and if they succeed with probability close to 1, then they must share not 1, but many EPR pairs, and they must have been measuring these EPR pairs not only in X and Z observables, but also other observables like Y or a Hadamard or this G. There's an interesting subtlety here that I'll just mention but gloss over, which is that you can only test these actions up to complex conjugation, okay? X and Z are real observables, so it doesn't matter. Y is a complex observable. Y and Y conjugate are not the same observables. But in terms of statistics, when you only see the outcomes of measurements, whether I conjugate my whole circuit or I don't, the statistics are going to be the same. So there is no way for a classical interaction to distinguish between whether the prover is applying the correct circuit or the complex conjugate of the correct circuit. I just wouldn't be able to do that. And that's fine, because at the end, I'm just interested in the outcome of the circuit like a measurement. And if I conjugate everything, the end is going to be the same. But you just need to deal with that a little bit and be a little bit careful. You can't really claim, oh, this prover has been measuring using Y. Could have been Y conjugate. Okay? It's just a small subtlety. And now we have the ability to prepare these magic states and other kinds of states that are required to sort of simulate the kind of protocols that I was describing before. And so here's how it's going to look like, delegation in this model. I'm going to do one of two things with probability half. Probability half, I'm just going to test these guys. So I just do my test, like this CHSH test or the more elaborate versions that I described on the previous slide. Do this maybe sequentially a few times and just make sure that the statistics are fine. And with probability half, I'm going to have them actually run the computation. And the way this is going to work is that, first of all, I'm going to talk to just only one of the two provers and tell that prover just to do the same thing as it would do in the test. So it doesn't actually know that now I'm doing the computation. It thinks it's doing the test. And so it's just going to have to do the right measurements, because otherwise it would fail the test. But then when I get the answers, I know what the state looks like on the second prover. And now I'm back at sort of like step 1 of the earlier protocols, as if I had shipped the qubits myself to this prover and it didn't know a priori what they were, other from the fact that it could measure them if it wanted, but that's taken into account by the soundness analysis of the earlier protocol. So then I just run this protocol for the second prover. I go back and forth. I do this classical communication, everything that we described before on these qubits. So let's run this on the example before I make some other comments. So now it's going to look like this. I have my two provers. Probability half, I just do the test, and the test looks like this. Like I just send random questions that basically tell you what observables you should measure. Z on the first qubit, H on the second qubit, G is like some other observable on the third qubit. Then you give me the outcomes, and I check. I do some statistics. Okay, that was the probability. And then with probability half, with the second prover, I'm going to do the exact same thing. So he doesn't know what's going on. I send labels that look the same, and it replies the outcomes. But now I know that as a result of that, the other prover has in memory a state that looks like the kind of state that we had in the other protocols. And now I'm going to use that in order to implement the computation by simulating the prepare and measure protocols that we described before. Okay, telling it which qubits should be the magic states, it reports the outcomes, and there's more communication that's going on, etc. So I just want to point out maybe that I'm glossing out over a few things here. One is your question from earlier, which is this is not actually what's needed in the protocol. I need something a little bit more complicated, right? It needs to have this Clifford on top of it. So you can ask, how do you test that? So you need to change a little bit the prepare and measure protocol to make this possible. I'm not explaining how. I'm just giving the flavor of how you use the two-prover assumption. And then at the end, the verifier is going to do the same kind of things, like check the traps and return the output. Okay, so that's how it looks like. This is what we described before. And so the properties follow from the properties before. Blindness follows. There's a little bit of a subtle point here, which is that blindness is going to hold as long as these two provers are not allowed to get together, right? And I was assuming that I had a one-round interaction with one guy and a many-round interaction with the other guy. And for the whole time, they're not allowed to come back together and sort of exchange information, because the first that I talked to actually knows the one-time pad keys. And so if it gets to tell them to the other one, then blindness fails, okay? So that's an assumption, and you can say, is it realistic or not, because I'm having this lengthy interaction. There's another protocol that I thought I was going to describe, but I think because of time I'm not going to describe due to Grillo, that gets rid of that. So it's similar to this, but the whole protocol is just a single round, and it's in the Hamiltonian model of computation. But it's one particular issue to just have in mind. And the verifiability just follows from the verifiability of the single prover prepare and send protocol combined with the statements that you get out of these self-tests, out of the CHSH, the analysis of the CHSH or the more advanced version. So once you have the two building blocks together, the rigidity and the single prover protocols, putting them together to get those is not too hard, as long as you have the right kind of protocols to start with. Yeah? No, not at all. So in fact, no. So what happens in these protocols, I think, is that you do the testing with much higher probability because the guarantees of this testing, state-of-the-art guarantees, are much weaker than the guarantees of the other protocols. So you do that more often because that's the part where you need to know that they win with probability pretty close to 1 before any theorem kicks in. So you need to do that multiple times. Whether the other part, you can be a little bit looser. Yeah. These are typically not super efficient, by the way, though it got much better in recent years. Yeah? Can you say a little louder? That's true. That's true. So there's going to be a separate mode for these protocols where you accept, let's say when you do the first step, right? So I'm going to accept the test, but then what's the outcome of the computation? I mean, I don't know because I did the test, right? And so there's going to be a separate mode. You're right. I have to change the definition and make it more complicated, where I'm going to, in that case, just accept, but not output any outcome for the computation. So I have to allow that for my definition. Another way to do it is to allow even more sequential interaction. And in that case, what I would do is I would do many rounds of tests. Instead of this half-half, I would do many rounds of tests, and that at a certain point, randomly chosen, stop and do the computation. And I'd accept at the end if all the tests accepted and the computation accepted, and then I can return the outcome of the computation. So that makes you fit back the original definition, but you have to do a longer interaction. Is there a proof for that? Not in the composable framework, for sure. I think in the two papers that are cited there, it's in the other model, so it's very standalone, kind of. So maybe Alex, if he's there, Grillo knows, but no, I'm not sure. Okay, if there's other questions, I have a summary slide about this, so let me pull up the summary slide, and then it lets you think about questions about that particular mode of operation if you have them. So just as a summary, what happened is that we used these self-tests to prepare eigenstates of Clifford observables, and it turns out that that's the only thing that's needed if you tweak the prepare and send protocols a little bit. We don't know how to do like a nice self-test like this for things that are non-Clifford eigenstates. So we know how to do it, but only in a very complicated way. The protocol that I described required many rounds of interaction. I went this over. There's a protocol by Grillo. But that protocol is in the Hamiltonian model, and it's not blind anymore. So we don't know if there's a protocol here that would be both blind and verifiable and involve a single round of interaction. And as soon as you have more than one round of interaction, it becomes very questionable because you could say they can talk to each other, and so as I mentioned, you lose the blindness. So I think this is something that would be desirable to have. Interesting question is that the total communication in this protocol is roughly linear in the circuit size. You could think that that's optimal. I mean, my circuit has a certain size. Surely I must exchange that much communication. Yeah, but in fact, there's no reason, right? The only thing that I care about is what is the outcome of the circuit. That's a single bit. Right? In classical complexity theory or cryptography, there are protocols that are similar like this that delegate computations that are very complex computations, where the verifier runs in time that's logarithmic or polylogarithmic in the total time of the computation. These kind of things that you might want to use on Google Cloud or something like this. And it would be interesting in the quantum case we could get such a thing. I mean, I think this would be a little bit extreme, but the computation at the level of the provers could run a polynomial size quantum computation, and the verifier would be extremely efficient, like polylog classical computer. In fact, I think this should be doable, but it's open for now. Another direction is that you can extend these protocols to verification of QMA languages. If you care, there you have to talk how the prover got the witness, but it's just something that you can do. That's all I wanted to say about the two-prover model, because saying more would be technical. I want to give you a flavor of how you go from the one to the two-prover. Are there questions? The next step is to go back to single prover and do we did prepare and send. I'm going to talk a little bit about receive and measure, because that's going to involve introducing this Hamiltonian model that I referred to a few times before but didn't properly define. Yeah?
So if you go from two-prover to multiple prover, will this improve things or not?
Not that we know, no. Not that we know. You could ask to make it more efficient or have better guarantees or be able to answer, for example, my first question on testing more. We don't know. Forever, forever. So if these guys get together next year, they'll reconstruct the one-time pad keys, and they might get information about my computation. It's a strong assumption. So in that respect, you could say, well, the protocol by Grillo is fine because it's good in all respects except from not being blind, but then this blindness assumption is assuming these guys are never going to talk, so that's a stretch, and so let's just forget about blindness and just care about verifiability for this model, yeah? Yeah, well, that's a complicated topic. If you're a computer scientist, it's related to things that have to do with PCP theorem. And so you encode the computation in a way that someone can do a complicated computation, but in order to check that they're doing the right thing, it's enough to do a few, very small number of randomized checks. Okay, so you have to figure out how to do that, but it's possible. In the classical realm, I don't know how to do it in the quantum realm, but I think it's an interesting question. Okay, so let me, okay. As much entanglement roughly as in the best protocols as the number of gates of the circuit, the total number of gates of the circuit.
So it's linear?
The number of gates, linear in the number of gates, yeah. Maybe there's a log overhead, like maybe n log n or something at most. So yeah, it's pretty good in that respect. Mm-hmm.
I have a small stupid question. At some point you mentioned that when you're doing the rigidity testing for Clifford gates and things like that, you have some complex conjugation that you're not sure that it's
Right, yeah, so you need to, yeah.
so in that, when you say y star, is that the conjugate of the...
The star was a reminder for me to remind myself to point the issue to you. So it just means that in the whole analysis, you're going to have to say things like, well, this prover either got applied a Y or a Y star, and I don't know which, and I have to make sure that that doesn't mess up.
So the Y is the polymatrix.
Yeah, Y was the polymatrix, yeah.
So, but then that's a mission.
Conjugate, not transposed. Oh, the star is not the same star as I had before. I'm sorry. By Y star, I meant Y conjugate, not transposed. Yeah, that's the ambiguity that you have. It might be conjugated and not transposed. So that's a different matrix. The eigenstates are flipped.
Things like that was the complex.
Yeah, before everywhere it was. I'm sorry. This star was actually an asterisk, like footnote, remind everyone. That's all. Yeah, sorry about that. Where's the question? Yeah? Exactly, yeah, exactly. Okay, so I'm going to move, okay, last one, then I'm going to move on. Yeah, go ahead. Can you say it louder?
So about the linear communication context, I suppose this particle achieves both blindness and verification. But if you just want one of them, can you do better? Do you know how to do better?
No. The question is, can I answer the before last question if I only ask about blindness or verifiability? And I think not. Verifiability definitely not, and blindness, I don't think so. Okay, let's move on. I want to tell you a little bit about this Hamiltonian model of computation and how it's leveraged to design protocols in this receive and measure model. So just to remind you what that model is going to look like now, we're sort of inverting. Like before, the verifier was preparing qubits and shipping them, and now the device is going to like set everything up for us, and then send the qubits one by one. We're going to measure them one by one, and then be done. Okay, so that's going to be the flavor of those protocols. It's known how to achieve them in two different models of computation. One is measurement-based, that I'm not going to talk about. They're very interesting, but I just didn't have time to talk about everything. So this is as much as I'm going to say about measurement-based quantum computing in that model. Instead, I want to talk something that's sometimes referred to as post-hoc model, or this Hamiltonian model, because it's also the model that we're going to be able to bring all the way to classical verification under computational assumptions. In that case, at a high level, what the device is going to be asked to prepare is not run the circuit or anything. It's going to ask to prepare the ground state of a certain local Hamiltonian that's derived from the circuit. Send this ground state to us one qubit at a time. And we, the verifier, are going to estimate the energy of this ground state by making single qubit measurements and check that this state has low enough energy. And if that's the case, then we'll get high confidence that the circuit produced a certain outcome. So I'm going to make that a little bit precise in a second. So here's the construction. I'm not going to explain how it works, but this is what it does. It takes as input any kind of a circuit on a universal gate set, a polynomial size circuit, and it constructs a local Hamiltonian for you. So this Hamiltonian acts on a number of qubits that's roughly the size of the circuit, like a little bit more for this thing that's known as the clock. But here are the important properties. The properties are that if this circuit was such that when I run it on the 0 input, it returns 1 at the output with high probability, let's say bigger than 2/3, then this Hamiltonian has a small eigenvalue, or it has a small ground state energy. And if the circuit did not return 1 with high probability, so with only 1/3, then this Hamiltonian is going to have a smallest energy that's a little bit above this A. This A is just a certain value that can be computed. You can determine what it is and also the delta there. So you can compute from the circuit both the Hamiltonian and the A and the delta. So I have to, moving into this model, I have to relax a little bit the way that I defined verifiability and blindness. First of all, we're going to get rid of blindness and only talk about verifiability now. And it's not in these models that in this model that the verifier is going to be able to reproduce the outcome distribution of the circuit conditioned on accepting. It's going to achieve something that's a little bit weaker, but for most general purposes is sufficient. It's just going to be able to distinguish whether this circuit typically returns a 1 or typically returns a 0, promise that one of them is the case. Okay? So from now on, we're only going to consider circuits that satisfy one of these two conditions, and our goal is going to design a protocol that allows us to check one of these two conditions and then go back to decide which of these was the case. Okay? A furthermore thing that's known about this circuit to Hamiltonian construction is that the Hamiltonian can be made into a very simple form where each of the terms is true local, as is only of the form x tensor x or z tensor z acting on different qubits. So it looks like this Hamiltonian looks like a weighted sum of xi, x acting on qubit I, xj, x acting on qubit j, and zi, zj. So it's just a linear combination with weights of terms that are like this, and I can compute what the Hamiltonian is, a classical description of it, and I'm trying to determine what the minimum energy is. And if I could do that to within small enough sufficient precision to distinguish between these two cases, that would tell me which category my circuit falls in. This gap there is, the delta is important because it tells me the resolution to which I need to estimate the energy. And typically in the best constructions based on Kitaev's work, the gap scales as 1 over the circuit size squared. And partially due to that, the protocols in this model are going to have a bit of an overhead in terms of complexity compared to the ones that worked directly in the circuit model. Oh, it's important for this to be feasible that the prover can prepare the ground state, the honest prover can prepare the ground state of this Hamiltonian. In general, a lot of you know that given an arbitrary local Hamiltonian, it can be QMA hard, so very hard to prepare the ground state. But for these specific Hamiltonians that are obtained from circuits, the ground state is easy to prepare and is a little bit more complicated than running the circuit itself, but not that much more complicated. Okay, so how is the protocol going to work? So that's the setup. The verifier computed the Hamiltonian from the circuit, and he's going to tell the prover what this Hamiltonian is. And this is why these protocols are never blind, because the first step is always going to be like this, like tell the prover what the Hamiltonian is. And if they have the Hamiltonian, they can reverse engineer the circuit from it. So let's just forget about blindness. I'm telling them what computation I care about. The prover is tasked with preparing a ground state of the Hamiltonian, which they can do using a slight variant of the circuit that underlies the Hamiltonian. And then send me this Hamiltonian 1 qubit at a time. Okay, and what I'm going to do is that secretly, I'm going to choose one of the local terms in this Hamiltonian. It's going to be either xi, xj, or zi, zj. And most qubits that are not I or j, I'm just going to say, well, I'm not interested in that, but I'm getting it because I don't want the prover to adapt what it's doing based on the term that I'm verifying. So I'm just getting the qubits, throwing away most of them. Oh, qubit I shows up. Okay, fine, qubit I showed up, I measure it. Throw away, then qubit j shows up, measure it, and then I look at the two outcomes. Because the terms look like this, I'm going to take the parity of the two outcomes, right? This is what xx or zz does, and then store that. And then repeat the protocol many times. Tell it, oh, okay, can you prepare the same ground state again and send it to me again? But then I'll check another term, and then I check another term. And if I repeat that a number of times, that scales roughly like 1 over delta squared, which now becomes the size of the circuit to the 4th. Overall, I'm going to have enough statistics to estimate the energy with respect to the Hamiltonian of whatever state this prover has prepared. And if I see that this energy is below my threshold A, I'm going to determine that the circuit returned 1 with 0, and if it's above, then we're in the other case. Actually, there's a little bit of an asymmetry here, so let me not get into it, but yeah. Okay, so very simple protocol. A bit overhead in terms of losing blindness, overhead of complexity, but this is the simplest protocol that we had seen so far. I guess I could have started with that. Let's do it on our running example. So the first step is to make this circuit into a Hamiltonian. So I don't know, you have to run Kitaev thing, and let's pop, you get a Hamiltonian out of it. So this is not the actual Hamiltonian, right? This one, ground state, is an EPR pair. It's just like a nice Hamiltonian. So let's imagine that this is a Hamiltonian that we want to check. So the first step is that we tell the prover, please prepare the ground state of this Hamiltonian, and the prover does it. In this case, it's an EPR pair. Then we tell it, please send it to me. And so the prover is going to send the qubits one by one. And secretly, I'm going to check, select one term that I want to check at random. Here there's only 2 terms, so I just selected one of them at random. I measure the first qubit, I get a certain bit. Then it ships me the second qubit, I measure, I get another bit. And then I take the parity of these 2 bits, and for you to have small energy with respect to this, the parity of the 2 bits should be 1 because I put a minus there, so this is what will give you the lowest energy. So here I wrote this check, but in general anyways, I would just estimate the statistics, repeat it many times, and then that's it. So the verifiability from this just follows from the guarantees of this circuit to Hamiltonian construction that says that if it is not the case that the circuit returns 1 on input 0, then there just does not exist a state that the prover could prepare and send to me that would convince me otherwise. And here, where are the qubits? Well, I'm getting them and measuring them, right? Okay, so summary, this is the communication, very efficient communication-wise, aside from the fact that you have to repeat the protocol many times. So that's the main overhead. It's an open question whether you could get a better protocol without such overhead. That might be challenging because it's open question whether the gap in that you get in the Hamiltonian, this delta from the circuit in the Kitaev's construction could be improved or not. Yeah?
So with more qubits, we sort of have or even with 2 qubits, we have an assumption that they're sending qubits in a similar sequence every time.
Yep.
And if that assumption doesn't hold, then they won't be able to convince us that the state,
Right, so the only thing they could do, so you have to be a little careful with the fact that I'm repeating the protocol, because you could say, what if they send me a different state at each iteration, right? But the point is that if the minimal energy is large, whatever state they send to me is going to have large energy. And so on average, you can think of the repeated energy estimation procedure that I'm making as computing very precisely the energy with respect to the Hamiltonian of a density matrix that is the average of all the states that I receive from the prover. And if I'm in the case where the minimal energy is too large, no density matrix is going to convince me otherwise. And in the case where it's low, yes, if it starts messing up the order, then I lose my completeness property, I'll reject. But I'm assuming that there we care about the whole. So this is a one-sided model. I mean, you're right to point this out. The model changed a little bit for the definitions of what I'm trying to achieve. And what I'm trying to achieve is just that if the circuit returns 1 with high probability, I want myself to be able to verify that, and that no prover can convince me otherwise if it's not the case. Convince me of that if it's not the case. Thanks. So if we were to look at the protocols in the MBQC model, these can be made blind. So that's another advantage that they have. And finally, we again have this question about fault tolerance, where now again the problem is, what if this measuring there is the measuring procedure at the verifier has some errors. The difficulty with respect to the one-time pad stuff is a little bit alleviated here because there's no one-time pad. And so there's a paper by Giorgio et al. Where they make the Hamiltonian model, the protocol that I just described, fault tolerant. The ones in the MBQC model, they again involve arguments that are similar to one-time pad. And so again, in that case, you have the issue, what if the errors are correlated to this one-time pad, then can you deal with that? And so fault tolerance, as far as I know, in that model is still open. Okay. So now we have about 15 minutes left. So I was going to say something about another two-prover protocol that's in the Hamiltonian model, the Grillo one that I mentioned earlier. I'm going to skip that, thanks to time, and get to the, so let me skip it. Close your eyes. And close your eyes. Okay, and get to the last step, if you remember the original outline, which is we have these simple protocols in the Hamiltonian model, and now I want to get rid entirely of quantumness at the verifier, make it completely classical. I could do that, as we described earlier, by splitting the prover and making it into two provers. But now I want to do it without doing that, just keeping a single quantum prover, getting an entirely classical verifier, and instead introduce a new kind of assumption, which is a cryptographic assumption that someone was asking about at the start of the talk. So I'm going to assume now that even the malicious prover cannot do things that are beyond just polynomial time quantum computation. In particular, assume that it cannot break a specific cryptographic scheme. And under that assumption, I'm going to get a delegation protocol, that's going to be similar to the one we just saw right now, this Hamiltonian model prepare and measure, but it's going to have one new ingredient. And here's the idea that we're going to, so we have like 15 minutes. I think that's just about time to cover that. You'll see more of it in Urmila Mahadev's talk tomorrow morning. So this is just trying to get a light introduction to warm you up for that. So we had this protocol, right, where the prover prepares a quantum state, sends the qubit one by one. I measure them in a basis that's unknown to the prover, repeat this many times, estimate the energy, and based on that, infer properties of the quantum circuit. I want to do the exact same protocol, except that I'm not going to get the qubits from the prover. Instead, I'm going to get what's called a commitment from the prover. So the prover is going to give me classical information that is going to certify to me that it actually prepared the qubit. I'm going to trust that based on arguments that I'll give to you. Once that commitment phase has ended, I am going to ask it for measurements in X or Z, depending on what I chose. And in that case, I'm going to tell it what term of the Hamiltonian I'm measuring. It'll know that. But because of properties of this commitment that I'll explain, it is not going to be able to change the measurement outcomes that it reports based on the fact that I told it which term of the Hamiltonian I was interested in. If it could, like the CPR Hamiltonian or some more complicated, it will always tell me something that makes me happy. But if it can't change it due to the commitment, then it'll be stuck. Okay? So I'll explain how we achieve that. So the first step is to, for those of you who are not familiar with this, is just to explain the idea of a commitment. That's an idea from classical cryptography. So there's just going to be a couple slides that are entirely classical, no quantum computation. We're thinking about a different task, but they're going to be relevant for what I'll say afterwards. Okay? So it's sort of a little aside here. So the setup is like this. Now we're into crypto land. So there's going to be Alice and Bob. So here's Alice, here's Bob. And Bob has a bit. And I'd like Bob to commit to this bit in the sense that I don't want him to change his mind about it later without revealing information about it. So I'd like Bob to be able to give Alice a certain classical value, C, like a string of bits, that it can have determined based on some randomness. So this R is a random string. I'll explain to you how this is done in the next slide. First, I'm explaining what I'm trying to do. Some C. And the first property, there's two properties for these schemes. The first property is that the scheme should be hiding. So whatever Bob happened to tell Alice at this stage does not reveal any information about the bit B that he has in mind. Okay? For example, it's a random string. Okay? But then there's another property. The other property is that time passes. It should be the case that after some amount of time, Alice can ask Bob to say, well, Bob, what is this bit that you had in mind when you committed at the first stage? Please tell me what it is. Of course, Bob could refuse to cooperate, right? That's totally fine. But there should be a way for Bob to cooperate, to reveal to her some information, like tell her what the bit is, plus maybe some extra information, in a way that Alice can determine what is that bit that Bob had. In a way, and here's a slightly non-standard way I wrote the security definition, but the way I wrote it is that it should be the case that as long as Bob doesn't do something arbitrary, for example, just walk away, right, and say, oh, I'm not telling you, then okay, fine. But as long as Bob is such that Alice accepts here, her flag accepts with non-negligible probability, a little bit 1%, then it should be the case that just based on that and based on the C from the first step, there is a unique B that is the B that Alice is going to return as her B star. Okay? So that's in the sense in which C commits Bob to a certain value. Later, he can decide to not reveal, and that's fine, but if he decides to reveal, there's just one value that he can't possibly reveal to, which is this B star that Alice is going to infer, and that depends on C, and that the value that Alice accepts. Okay. So those are the requirements. I mean, I could say a lot about these requirements, but let me say, I think it's going to be more useful if I tell you how we achieve this, and it'll also help you understand the definition. There's many ways to achieve this. There's also many variants of this definition. I just chose one particular variant. The way that's going to be relevant for the quantum version is using something that's called Claw-free functions. For those of you who know, it's like a slightly refined version of a collision-resistant hash function. But here's what it is. It's just a pair of functions. It's like classical functions, like from n bits to n bits, that has special properties. The first property is that both of them are bijections. And because both of them are bijections from the same domain to the same range, it's going to be the case that any point there in the range has exactly one preimage, it's a bijection by f0, and exactly one preimage by f1, okay? And then the other requirement, that's the security requirement, is that it should be computationally difficult to identify any triple of points that forms what's called as a claw. So any R0 and R1 and C, such that R0 and R1 are mapped to C. And now we're kind of in crypto land suddenly, so there's some operations that are easy, some operations that are hard. So it should be the case that these functions are easy to evaluate. So for example, it's definitely easy for me to find R0 and C, such that C is the image of R0 by F0. That's easy. I just choose R0, compute the function, get C. And I would do it. What's hard is to find also R1 that gets mapped to the same C. Okay, and by hard is that I'm making an assumption here. The assumption is that I'm going to set up these functions so it's easy to evaluate you, but the best algorithm I know that would achieve this is exponential time, and so I'm going to make the assumption that it's hard. That's just a crypto assumption. Okay. This is what I was just saying, sorry. So I'm not going to explain how to construct these functions. I think you might hear about that in other talks during QIP. Just to give you a flavor, you can construct them on a problem from crypto that's called the learning error problem. And how they look like, just high level, just get the idea that these functions are actually very simple. They're not like super complicated function. What they do is basically matrix multiplication. So you think of the left-hand side, these n-bit strings as n-bit vectors. And what the function does is that it basically hits the vector with a fixed matrix, but then it muddles that a little bit with what's called an error, and I'm not explaining where this error comes from, but it does matrix multiplication a little muddled. And the other function does the same, like matrix multiplication, a little bit muddled, but then there's a shift. And this shift is going to be what governs which pairs of images get mapped, pair of points in the domain get mapped to the same image. They're going to be related by this shift. And the learning of errors assumption says that if you're given noisy equations like this, so points in the range, it's generally hard to find a preimage. Like if you're just given equations in a vector, you can invert the matrix and recover the thing. But if you're given noisy equations, everything breaks down. Like your Gaussian elimination algorithm just breaks down. And so the security assumption behind that is that not even quantum computers can invert systems of linear equations when the linear equations are given not exactly, but up to a little error. So I'm saying this very imprecisely just to give you a flavor of the assumption. It's not like something that looks very wild. It's a sort of nice-looking assumption. Okay, so let's assume that we managed to construct this pair of functions that has these properties. Let me explain how you commit to a bit, and then let me explain how you commit to a qubit. Committing to a bit is pretty straightforward. Here's how it's going to work. So we have Alice and Bob has his bit. And what he's going to do is that he's just going to choose a random point in the range, in the domain, and then evaluate either F0 or F1 on that random point and send it to Alice as the commitment, okay? So the commitment is the value on the right-hand side. I made the right-hand side smaller there. There's no reason. It should just be the same side. And send that to Alice as the commitment. I can already check that this scheme is hiding. This value C doesn't reveal any information because whatever B was, FB is a bijection. If the point on the left is chosen uniformly at random, the point on the right is uniformly at random. So this C is exactly uniformly distributed. No information about the bit B has transpired. Now later on, Alice is going to ask me, well, what is this bit B that you had in mind when you gave me this string C? Can you please tell me? There's an easy way I can tell her. I'll just tell her, well, this is what it was, right? And why don't you check? And here's how you can check. I'll tell you what the preimage was. So I'll tell you what R was, and then Alice can check that this R will map. And the reason this scheme is binding is by the assumption that I made in the previous slide. The assumption that I made in the previous slide is that it should be hard to find a point in the range, C, and two preimages that map to it. That's exactly what Bob needs to change his mind, okay? To be able to change his mind, he needs to be able to find a point C in the range, and later, depending on his mood at the time, to be able to give me a preimage according to the F0 function, to pretend he had chosen a 0, or a preimage according to the 1 function, to pretend that he had in mind the 1 function. But if he can do both, with some non-negligible probability, then I can run him many times in the two different moods, and I would get C and R0 and R1. That's this claw that's supposed to be hard to find. Okay? So it's computationally difficult for Bob to change his mind once he's given C, or at least to have the ability to uncover two different values that he would choose at the later stage. So this stuff is like well-known stuff in classical cryptography. It's used for a lot of things like zero-knowledge protocols and other kinds of things. Here we want to use it to commit to a qubit. So let me try to explain a little bit of this. It'll be some of the last things that I say. So what I have to say even what do I mean by committing to a qubit? So what's the setup? Bob has a qubit. I'd like ignore this. This is how it's going to work. But I'd like Bob to send to Alice a classical string that supposedly commits to that qubit. It should be hiding just as before. So this classical string should not reveal any information about the quantum state now. Then we could wait. And now there's going to be a difference, okay? Because the difference is, okay, now I want Bob to reveal the qubit. Yeah, okay, what does that mean, right? Because if Alice is classical, which is what I'm trying to do, right? Later, Alice is going to be the verifier. He can't send the qubit. A qubit is a qubit. It is quantum. Alice can't read it. But thinking back at the protocols that we were thinking of, I don't really care to see the quantum state, right? This ground state. What I care really is that you tell me what would happen if I measured it in X or Z. Okay? So this is what I want of my qubit commitment protocol. There's going to be two different possible things that Bob could reveal. Alice could say, please measure the qubit that you committed to earlier in the computational basis, this is the Z observable, and tell me what outcome would you get. And there should be a way for Bob to tell me something that allows me to recover a certain value A that is supposedly the outcome of a measurement on this qubit in the computational basis. And I should be able to do the same thing in the X basis. Not the two of them at the same time, of course, right? Because this qubit can only be measured in Z or X. But I, Alice, should be able to ask Bob for the one or the other. And there should be a way for him to communicate to me this information. Of course, he could refuse to participate as before, but there should be a way for him to communicate the information. And now what's the binding property? The binding property is interesting. What's really important to me is that Bob can't communicate to me measurement outcomes that depend on the basis that I'm interested in. For example, I wouldn't want it to be the case that this protocol can be played with a Bob that cooks up a certain state. Okay, then it commits. And then when I ask Bob, please measure in the Z basis, tell me what you got. And Bob says, oh, I got 1. But if I tell it, measure in the X basis and tell me what you got. And then he also says 1, all the time. That shouldn't happen, right? Because there's no state that can be measured in X and Z bases, always say 1, that the uncertainty principle, that doesn't exist, right? So I want my protocol to exclude these kinds of things. And here's an informal statement of the binding property. I'd want it to be that for any Bob that accepts to participate in this protocol, okay, that doesn't get rejected, so it gets accepted with non-negligible probability. Then, after the C has been sent, there exists somewhere in the sky a quantum state that I could define, such that later, whether I ask for a Z or an X measurement from Bob, then the outcomes that Alice gets, decodes in the end, AZ and AX, are distributed as outcomes of a measurement on that quantum state. So for example, if this binding property holds, this rules out the example that I gave you just before, right? Because for that example, where Alice would always return 1 and 1, there does not exist a quantum state that underlies such a distribution of outcomes in the Z and the X basis. So I was going to tell you how to do that based on the functions, but I think we're running out of time. So maybe I'll just show you, you'll learn about it more tomorrow. I want to go back to the protocol and explain if we had such a commitment protocol, how we'd be done. And then that's the last thing I'll be able to say. So this is explaining how the functions are used, but I'm going to skip that picture and go back to the protocol. So here's the protocol that we had earlier. Okay, if you remember, the prepare and measure protocol. Verifier computes the Hamiltonian, sends it to the prover. Prover prepares the ground state, sends the qubits one at a time. Verifier secretly, this was important, selects a Hamiltonian term to measure, measures it, and then repeat a large number of times to estimate. Okay, this is the quantum verifier. Now I'm going to make the verifier classical. keep the first two steps. The first two steps are the same. I tell, and this prover is supposed to create this ground state. But now what I'll tell the prover is please commit to having prepared that state. So 1 qubit at a time. You prepare the ground state. This is many qubits. But for the first qubit, run this commitment protocol and tell me a classical string, C1, that commits you to it, and then I get it. And then the second qubit, C2, etc., and I get all these strings. And now the prover is committed to that. Now I'm selected, I wrote secretly, but it doesn't matter that it's secretly. Verifier decides whether it's going to check an X term or a Z term. And then I'm just going to ask this prover, like, please tell me, like, just do it. Like, do the measurements and tell me what the outcomes are. Reveal to me measurement outcomes of this qubit that you were hiding in the X or Z basis. Then I'll record the outcomes, and then I'll repeat the protocol a polynomial number of times. And that's it. And if your qubit commitment protocol has been set up in the correct way, which is what we'll hear about tomorrow morning, how to do it, then this guarantee will be enough. The guarantee is not a guarantee that says directly the prover must have been saying this. It's a little bit weaker. The guarantee was there must exist a quantum state that analyzes these measurements. But that's the only thing that I need in order to estimate the ground state energy of this Hamiltonian, right? If you remember this Kitaev circuit to Hamiltonian construction, I only needed to have the guarantee that the quantum state exists that would have given to me, this is a little bit your question earlier, that would have given to me these measurement outcomes. Okay, and then I repeat a certain number of times. I don't know if we need to run through the, oops. Oh, no. Okay. Run through the running example very quick. I mean, we went the same example as before, same protocol as before. The only difference, let me skip it, because the only difference is that I just explained it, I think, enough on the previous slide. Let me also skip that, and I'm out of time. Felix said that because we started 5 minutes late, I could take 5 minutes. I don't want to take 5 minutes. I just want to take 2 minutes to tell you about my coda, just to go back to the open question. And so I'll just conclude with that, right? This is just to motivate you on this open question as one of the most beautiful open questions in the interface of complexity theory and quantum computing, which is whether you can go one more step and get rid of this computational assumption, okay? Do the same thing, but not assume that the prover has bounded computational power. This is open. And I just want to say a few words about it because some things about it are not open, are known. There are some problems for which we have efficient verification. For example, did I write it here? This is the problem factoring, right? So this is a question that comes up often, which is, well, if you're interested in verifying quantum computer, why don't you wait until this computer could factor and then tell it to factor, and then you'll know that quantum computers are more powerful, right? This is okay if you're interested in factoring. But for all we know, factoring could be easy on a classical computer, and so that's the one thing that I'll know at that time, right? That the quantum computer has figured out a way to implement factoring more efficiently than I thought was possible. So I really want to check the whole of quantum computation. And not every problem that has a quantum circuit is a problem that is like factoring, that has just a classical witness that can be verified efficiently. An example is this recursive Fourier sampling problem I introduced, I think, by McCaig or something. One thing that is known, and that's the one thing that I wanted to point out to you because it's relevant if you're interested in this question, is that if we consider the model of interactive proofs, where it's not only like factoring, where I'd get a proof, like the factors, and I'd be able to check it, but I can interact with the machine, as we were doing throughout the whole tutorial. It is known that every problem in PQP has a classical interactive proof that allows you to decide whether the outcome of this circuit is 0 or 1 using a classical polynomial time verifier and classical communication. The reason this does not solve the open question is that in that protocol, the actions that are required of the prover in order, even in the honest case, in order to convince me that this computation had a certain outcome, are not physical computations. They cannot, for all we know, be implemented in the quantum computer. You need more power. And so these protocols are sound, they're verifiable, they're fine, but they're not complete in the model that I described before. I can't run them with a quantum computer. I could run them with someone even more powerful, which is a bit strange, because you say they're more powerful, they're going to cheat more. But no, these protocols leverage a certain way to verify computations. That's not the way that we've described so far. That involves encoding computations in polynomials and doing computations with these polynomials that we don't know how to embed into a quantum computation so as to make even the honest prover efficient. And so that's an open question whether you could do that, but now I'm really seriously over time, so I think it's a nice way to end on this open question. So I'll stop here, and if there's questions. I don't know if...
Thanks a lot, Thomas, for that tutorial. Are there any short questions? Yes, there's one.
So, if the prover is honest in the previous example, they want to produce a ground state which may have a lot of entanglement, and it's not obvious that the commitment procedure doesn't disclose it.
Oh, yeah. Yeah, these things are very sensitive, and if you don't have a fault-tolerant quantum computer, I doubt that you could implement it. You're right. My protocol called for preparing a ground state, which is a very complicated state in general, and then on top of that, one qubit at a time, doing a certain procedure that I didn't have time to describe, but that also involves like some kind of a computation on these qubits individually, and I need to make sure that I don't destroy any of the entanglement as I'm doing that. It could, but if I had a fault-tolerant quantum computer, there's no reason. I mean, the computer is fault-tolerant. By definition of being fault-tolerant, I can implement any quantum computation without destroying the state, and this is what I'm doing there. In the end, the whole computation that the prover does is a quantum circuit, including preparing the ground state. It's just a big quantum circuit. So, you know, if my computer, I mean, you might be pointing out that it is a complex computation, and that is true. But if I do have a fault-tolerant quantum computer, then I can run the protocol.
There's one more question up there on the balcony. Maybe short, please.
Oh, hi.
What's the third bullet point true?
Here? I mean, it's the definition of MA. I meant it to be the definition of MA.
If a BQP machine can solve a problem, that doesn't mean it can find the MA weakness for that problem.
No, I just wrote efficiently verifiable solution. But you're right. So I think what I wrote is correct, but you're pointing out that even though what I wrote is correct, it doesn't answer the broader question because that witness might not be efficiently, it might not be efficient to find it. Yeah, good point. Yeah, thanks.
All right, let's conclude the session and thank Thomas again for a great tutorial.